All right. So what we have over here is we have the image. Okay. So let me create a Jupyter notebook file and then see how we can manipulate the image we just created. So we need a few libraries over here, okay? And then there's one that we are going to use, and that's what we call the Python image library. Okay. So we are going to use a Python image library for whatever thing we are going to do now. So if I'm to do Python image library, if we read around it, yes, so that's PIL. So Python image library is a standard library that we use for processing images and stuff like that. So I can do a simple analysis of this and I can say from the Python image library, I want to import this over here as image, okay? And then I also want to import NumPy as NP over here. So let me run this and then we are going to do some few tests over here. So remember I have this image, this is the test image.png in this folder, so I can bring it over here. And in this particular instance, this is going to be our data image. So let's have a variable called data image, and it's going to be from, I'm going to use this image, okay, class I'm getting from the Python image library. And then I can do image dot okay, let me do okay, so image dot I think I've forgotten the name of the method over here, but we can figure it out over here. Um, oh, what is happening? I'm not seeing whatever thing I'm looking for, but then let's see. Okay, so let me see image dot I think I don't think load is in here. Okay. Okay, I think image dot open, I believe so. So we have, what do we want to open? We want to open this test image, okay? So I'm gonna have test underscore image and then dot .png. The file extension is very important. So I run this and then if I'm to check out the data image, this is the data we worked with, okay? All right. So one of the things, okay, we can do it this way. So now we've loaded the image. Now I want to see the metrics version of it because one of the points we've established is the fact that this image, as the computer sees it, goes beyond this, okay? The computer basically has some grid around this, and each grid, let me see if I can bring this up over here. And after that, I'm going to clean it, but I just want to show you so that we get this fundamental concept very well, and then we get into building of the models. So what we can establish is the fact that as far as this image is concerned, the computer does not see red, green, blue, or yellow. Okay. What the computer sees is, okay, I know that there's an image and I know that there's a grade. Okay. So let me use a different color. So let's say yellow. So this grade is basically, oh, sorry, the lines do not look nice. But kindly bear with me. Let me use maybe the black color. So let's say this is a grid. Okay. So there's a line. Okay, this is one, and then there's another. Okay. And they could be many because look, some of the things we hear when we have some images or when we have some cameras, okay, this camera has the capacity of maybe taking pictures in 20 megapixels, okay? So 20 mega times 10 to the power 6 in terms of that grade. So they are very, very tiny, but then at the end of the day, they'll come up with a structure like this. So the computer will look at this image and see that, okay, for this particular grade, I don't know A, B, C, D, or I don't know images, but I know 1, 2, 3. So in terms of numerical representations, what I know is R, G, and then B. And for the R component, I know that, okay, the R component is very intensive over here. So maybe the R component is 255, okay? And then I don't see any green or mixture of green over here. So the green is going to be 0. And then the blue is also going to be 0. So this is going to constitute an array, okay? So this one is going to have its array, this one is going to have its array, this one is going to have its array, and at the end of the day, it's going to constitute a very large matrix, okay? Because as far as the relationship of arrays and matrices are concerned, you realize that when we have a one-dimensional array, okay, we have it as either a row vector or then a column vector, okay? So those are the arrays, okay? And then when we put two or more arrays together, then we are getting um, um, how do you call it? A matrix, okay? And then we have the other ones we call tensor. So tensor is basically a matrix of higher dimensionality, okay? And that's where we get the word TensorFlow. So that's where Google derives or takes inspiration for the word TensorFlow. So that's what we have over here. So in terms of what we just illustrated, how then does the computer also see this? Now, what we have over here, this image data, which is showing us this image, we can more or less do a typecasting of this into its array equivalent. And when I say
Uh,
typecasting, we know what
uh,
we did back in
Ken,
the day. So
Ken,
we can
Sheriff
add
wants to ask a
something like
question.
maybe
Somebody is asking a question.
um let's say age is equal to, and I'm putting this in some double quotation mark. So when I do 12, we know that age, the data type of age as it currently stands is a string, okay? But I can do, for instance, maybe a typecasting of this. So I can do maybe age is going to be equal to, and then I can do int, and then pass in age over here. And now this age, which is a string over here, is going to be converted into an int and then saved back into the variable age. So now if I do a preview of age, I mean, we did this over and over again. Yes, we are going to see 12, but then this 12, if I'm to check the data type of, if I'm to check the data type of age now, we are going to see that this is an int. We've done a typecasting. We are going to do a typecasting over here because the data type over here, this data image, if I'm to check the type of data image over here, we see that this is something from the Python image library because that's exactly what we did, okay, to open this up and then save it up over here. So I want to do a typecasting. And the typecasting I want to do is I want to convert it into some NumPy array, okay? So that's
Ken,
why I've imported NumPy over
somebody
here.
wants to ask a
There are
question.
several ways of
Somebody,
doing this. This is just one way. And when we build a model, I'm also going to show you other ways we can also achieve the same process. So at the end of
somebody
the day,
wants to
let's
ask
say I
a
have,
question.
let's say array data, and that array data is going to be in np.array And then what do I want to pass in? I want to pass the image or the data image. Remember, this is passing through a NumPy array, which is almost like doing a typecasting, okay? Just as we saw with the int over here. So now when I run this, we don't seem to have any problem. Now let's do a preview of the data array as we have over here. Excuse me, just a minute. Hello, sir. Oh, okay. Okay, sorry. Okay, all right. Sharif, my attention has been drawn to the fact that you want to ask a question. Please, you can proceed.
Yes, yes, sir. It was about the TensorFlow story that you gave.
Okay. All right.
Yeah, I
Okay, I
didn't
can
really get.
also see it in the chats. All
Yeah.
right. Okay, so well, the first time I heard of TensorFlow was because I was quite interested in some of these things, and I realized that look, this is a library I can use to build models, okay? But then the inspiration is just like maybe Elon Musk having his Tesla company, okay? We know back in secondary school what Tesla is, okay? But then somebody has adopted that brand of a name and then developed some powerful systems with it. So the word tensor in itself, if you are to look at the word tensor, okay, in itself, it says mathematically, tensor is an object like, okay, generalized scalar vectors, whatever, okay, and matrices. But in terms of dimensionality, okay, when you have something of a rank 0, then we are dealing with some scalar quantities, okay? So we know what vector quantities and scalar quantities are. So a scalar quantity is a quantity that has only magnitude, okay? And then the vector quantity will have magnitude and then direction. Those are secondary school stuff, okay? So when I say the number 2 is just scalar. It only has magnitude 2, maybe 2 kilograms or 2 whatever, okay? But then if I put numbers together and then maybe 2,5, okay? That 2,5 that I'm referring to, maybe 2,5. That 2,5, okay, in some simple terms, the 2 can represent the magnitude and then maybe the 5, the direction, okay, depending on how you look at it. Okay. So if the rank, or in terms of dimensionality, we up it up a little bit, then we are getting what we call a vector. But then when we up the dimensionality again, then we are getting what we call a matrix, because a matrix will definitely have the rows and columns. And then when we up the matrix in terms of dimensionality, that's where we are getting into the realms of tensor. So a tensor is a matrix of high dimensionality. That's basically the fundamental concept. And the point I make is um, TensorFlow is a library developed by Google. Okay, so I think they took inspiration from this, that look, we are going to work with matrices of high dimensionality. So we want to have a befitting name for it. That's basically the history behind that. But then you can also do your own personal readings about that, and then yes,
Okay. Thank you very much.
you are welcome. So back to the point we have over here. Now we have the data over here, okay? And now when I do a preview of this and I run this, we get the numbers, okay? And we get the numbers because, yes, it was this original data, but then we did a typecasting of some sort, okay? Pass it through a NumPy array, and then we are getting the data representation of it. All right. Now, I want you to pay attention very well. Look, this is the image we worked with, okay? And this is the equivalent of its tensor or matrix representation. Now, it is important to note, and that's why I was very particular about some of the numbers I chose over here. Look, I wanted to prove a point that, look, the numbers that are going to be generated are not just going to be random. It's going to be based on the image you brought in. And the image we brought in had at least, just look at the bigger picture. So at least there's going to be some, how do you call it? Some grade, okay, on this. And on each grade, let's say this is the first grade. The first one I did, let's see, this is the first grade, okay? And there's another one. And then, so we said in terms of number representation, this is a pure red. So we are getting a 255 for R. Remember, it is RGB, okay? We are getting a 255 for R. Maybe a 0 because it was purely red, okay? And maybe another 0 for blue. All right. And that's exactly what we see over here when we get into the proper numbers. Because look, this is like 254. So maybe it was just a little bit faint in terms of the intensity over there. And then you see that the other representations, which is the green and then the blue, are now set to 0. So this is not just some random numbers that have been generated, but the actual matrix representation from the RGB. Okay. So that's exactly what we see over here. And then the other ones to also follow up based on the dimensions. Okay. Now you can see that with these ones, you see that yes, the 255 is also quite intensive. I mean over here, but we have a little bit of the green and then the blue showing up. And I believe those ones will be the ones at the edges. Okay. So when you critically look, definitely the edges are not going to be pure red. There's going to be some overlapping of these colors, and that's what you see over there. All right. So this one is a very huge tensor. Okay. It's a matrix of a very high dimensionality. And we can check the dimensionality. One of the easiest trick to check is, look, you just count the number of opening brackets over here. Okay. So if I'm to do array underscore data dot end dime, this to check the dimensionality, this of 3D, okay, or the dimensionality is 2 over here. Now, one of the interesting things we can also check is beyond the dimensionality, you can also check the shape. And these things will come in very handy when we start building these models and we see that, look, if something is not right, you are probably maybe missing out on a shape or something like that. Okay, so when I do array underscore data dot shape and run this, we are getting this. So one of the easiest ways to look at this, okay, is as far as matrices are concerned, okay, there's always going to be some row components and then some columns in there, okay. So the first number you see over here, that's 306, is the number of rows we have over here. So in this particular image, okay, in this particular image, you are going to see that it's going to have, or what the shape is trying to illustrate to us is the fact that it is going to have 306 rows. Okay, so the lines I was drawing is going to be 306 in all, and then the number of columns is going to be 531. Okay, 531. And this three we have over here is the color channels. And those color channels are the RGB. So in some images that we are going to work with later on, okay, we are going to realize that maybe those images are going to be in black and white. So for black and white, the color channels are not going to be three, okay? So the colors have been stripped off, and then we are not going to have three color channels, but then something that when we get there, we are going to see. So those are the numbers we see over here in terms of their representation. And it is very important we understand these things because look, when we start building the model, which we are going to do in the next minutes, we are going to see that missing out on dimensionality is very important. Okay, if we miss out on the dimensionality, we are going to run into problems because, as we already know, when we are dealing with matrices, when we are trying to multiply matrices, we need to check for dimensionality. Okay, when we are trying to do things with matrices, whether we are broadcasting or adding or subtracting or any other thing that we intend to do, we need to make sure that the dimensionality of the matrix is in shape. All right. So now that we have a fair understanding of this image and what it means and stuff like that, now let's go into the proper building of the model to get the gender classifier. And
Please,
like I did indicate, I think, yes, that's over here. So let me just share this. Um, Let me
please, I
share
have
this
a
with
question.
you.
Yeah, please go ahead. Somebody has a
So
question. Go ahead.
Control C, and then I'll put it in the chat.
So
Control C.
I tried downloading one of the
What I want to do, like
images
we always
with
do,
the
is
great
I want
colors.
to click
Hello?
on code and then download this. Okay. So I'm going to download the zip file. Now, the interesting thing over here is with this particular one, we gathered some images. Okay. So we have some images for training and then testing. So for instance, if I go into the training file, you are going to see that I have females and then I have males. So you are going to see all that, and then we are going to build a model to learn the features from females and also the features from males, and then we move on. All right. Kindly give me a second. Hello. Oh, sorry. Let me listen. Okay, please. I'm told someone is asking a question. Please, you can ask again.
Hello, sir.
Yes, Sherry.
Yes, please. Can I share my screen? I want to show you something for some explanation. The great colors.
Okay, no problem.
Yeah.
So you can.
I don't have the permission.
Okay, let me try and see. Okay, I think you can now share your screen.
Okay. Please, sir, can you see my screen?
Yes, it is loading.
Okay.
Okay.
Yeah. So I just downloaded this image from Google, and
Okay.
I tried to apply what you were saying on it. So changing it to the array form.
Yes.
So my question is, see the first tensor. The first tensor is saying 000.
Yes.
I am presuming that that's referring to the first black color. Uh-huh. And the next one is also so we have 111666, and that one is somehow black, but it's okay.
Yes.
And the third one is where I have my question. I'm seeing black again, but when
Okay.
I refer to the image, I'm seeing somehow white.
Okay. So you see, the issue here is scroll down. Let me show you something. Okay. Now, what you have over here, okay, if you pay attention to the first set of numbers or the first set of arrays that we have over here, where we have the how do you call it, the 0000, okay, that's a black. Okay, you see that there is some kind of
Yeah.
okay, comma. So it is more or less truncating the entire spectrum. I don't know if that makes sense. Okay,
Mm.
so you are not really seeing the whole thing. That's the point I'm trying to make. Because
Okay.
so there's some truncation, and then some other numbers are also hidden somewhere. So you are not seeing that. So it will be very difficult. And that's why I was very particular about the first one, because the first one is definitely going to be the first number that we are going to see. But because it is a very huge matrix, things are going to be truncated. So we cannot
Mm.
track each and every number. That's the difficulty
Mm.
you are going to have over here.
Oh, okay.
All
Okay.
right.
Thank you very much.
You're welcome.
So if you want to check, you can look at the dimension or the size of the image that you have. If you look at the size, it will tell you maybe X by Y by Z. The Z there is for the number of colors, which symbolizes the RGB, three primary colors. So if you have a matrix that has maybe 800 by 1000, 800 by 1000 means you have 800 rows, 1000 columns. And if it is by 3, it means that for the red color, you have 800 by 1000. The green, 800 by 1000. The blue, 800 by 1000. Now, the integers that you are going to get, if you take red, there are different shades of red from 0 all the way up to 255 shades. So those shades are the integer values that you are seeing in there.
Mm. Oh,
So
okay.
because you are not seeing all, like Ken said, otherwise, if you can find a way of saying, I want to see the first 1,000 elements, rows and columns, then you can see that.
Mm. Mm. Okay, Prof. Thank you very much, Prof.
All right. So let me continue. But you see, with regards to seeing those things, okay, you know that we can use the slicing technique, okay, to get them, or at least to get a number of them. So for instance, if I do this array data, is going to show me everything. But then if I bring in my square bracket and maybe do a colon, and for instance, maybe 100, okay, that means I want to see the first 100, okay. But it will be, once again, you see, things are also being hidden over here because of the nature of how big things are looking. Okay,
Mm.
so at the end of the day,
Mm.
things are going to be hidden, and that's the point I make earlier on, that most of the things that we are going to do is almost going to depict like the black box model. Okay, so we are just going to feed things in there, but you just need to, in fact, it is very important you have an understanding of it, so that when something is broken, you can fix it, or when something is not giving you an output that is required, you can actually figure it out and then work things out.
Yes, sir.
All right. So
If you wish, what you can do is you can load that image in MATLAB, and
mhm.
then you can see all the data values in there.
Uh, okay. I'll try that, Prof.
Yeah.
Thank you very much.
Okay, so thank you. So let's continue with what I have over here. So what I ended up doing was I've shared a link with you. Okay, so I've downloaded the CNN image classifier file. So let's go back into my downloads. I have it over here. Let me do the extraction and then we'll start working our way up. So fortunately for us, we already have the images and everything over here. So once you have this downloaded, you don't have to worry so much. All right. So this is the image data folder, and then like you can see, we have training part and then the testing part. When we go into the training part, because there's an image classifier for male and female, that's what you have over here. But if you are building a system where maybe you are doing maybe fruits classification, okay, based on colors or based on the images of the fruit, then for every class you need some stack of images over here. So when I open this up and go to the males, these are different variations, and I managed to make sure that, look, I have different races and other things, okay, because males have different versions of males. So for instance, this a white man, another white man smiling, okay. This is maybe a dark Asian man, this a typical black man, a white man, different, there's a black man. So different variations of human beings, so that we can get the features of a typical man. Okay, so these are the images I have. Now I've labeled them and I have about 18 of them. Okay, all right. So this is 18, and then when I go into the females folder, I also have I think yes, 18 of them. So once again, these are females, different races. So the first two are black. This one too is a black female, another black, and these are white, Asian, and different females over here. All right. So this is the image, or these are the images we are going to work with. Okay. So what I'm going to do is I'm going to open up my Jupyter Notebook environment over here, and then we are going to see how we build a classifier to understand these images, okay, and then we are also going to make predictions. So look, the interesting thing over here, and this is what makes this work very interesting, is the fact that the images that we are going to use to train, okay, none of them includes our images. So the system will train, and then we are going to use our own images to test. So to actually know that the system was able to learn very well. Okay. All right. So let me create in a new notebook over here, and then we are going to work with this. So we are going to import the libraries that we are going to use. So for the libraries, we are going to use quite a number of them. Okay. So for the libraries, we are going to use a number of them. So let's import, so let's do Keras over here. And for the ones that you don't have them installed on your system, you just do a pip install and then the name of the library, you'll be fine. Now let's do CV2. So CV2 is an image library. Okay, so in the first one that we're trying to import the image and stuff like that, we're using the Python image library. Okay, CV2 is also another one. Now CV2 gives us the opportunity to even use our cameras to take images and stuff like that, which is something that we can do. Now I also want to import scikit-learn over here because we are going to use scikit-learn. I also want to import NumPy as NP because we are dealing with matrices, so we are definitely going to fall on NumPy. And then maybe for plotting, let's import matplotlib. So I'm going to say from matplotlib import pyplot as plt. And then, yeah, so inside of Keras, there are some libraries that are very important over here. So let me bring those ones out. So I'm going to say from Keras dot preprocessing dot image, I want to import, and these are ones that we are going to use. I'm going to use the image data generator. We are going to see what this is going to do, and I'm going to give it an alias as IDG. So import image data generator as IDG. And then the next one we are going to do is I'm also going to say from Keras dot preprocessing. I want to import image, this one. So I'll do a shift enter and run this, and hopefully I don't have any problem over here. Okay, it's taking longer than, okay. These images are quite heavy, so when you're importing them the first time, all right. So I think just about now, everything is looking good. Okay. So just as we're using Pale, which is a Python image library to upload stuff and things like that, like I said, I'm going to show you another way. So let's say the data, okay, of the image that I want to work with, I can bring in image dot load underscore image over here. No, load img, and then I bring in the path. So over here it is a path, and let's pay attention over here to this path. Remember, we have this image data folder over here, and inside of that, let me open this up over here. We have the image data folder, and inside of this, we have, for instance, the training data, and then we have, for instance, mail. Okay, so it is a path we need to navigate through one after the other. So in order to go through this, we can come in here, mails, and then get it over here. So there's a entry point. You want to go through image data training and then mails. So I can copy this and then bring it down over here. and then paste this over here this way. Now, this is just going to get to the folder. So when I do another slash, and then maybe um the name is, for instance, maybe mail2.png, okay, and then I run this. I have a problem over here. It says there's no file directory as this. Okay, so let me go back into the folder and check. Okay, this is mail2. Let me check maybe. Okay, so the file extension is JPEG. Okay, so JPG, GPJ. It's not PNG, so I need to go and change that. So JPG like this, and then when I run this, now I don't have any problem. So now when I do a preview of the data, I have this showing up over here. So this is the image. That's image 2. Okay, this one. When I do image 3, this man is going to show up. So let's do image 3. Image 3, and then we have this one showing up over here. All right. Now, one of the things we also need to understand, okay, is look, whenever we do the conversion of these images into the NumPy array and we are working with the look, one of the things we need to be mindful of is the dimensionality. You see that some of the images appears in portraits, others are in landscape, and you can see that the dimensionalities are not the same, okay? So you can see that when I hover around this particular image, okay, this black man over here, you see that the pop-up that shows the dimensions is 600 by 397, okay? That's definitely going to be different from the 736 by 1102 dimension I have for mail 3. So we want to have a system where all the images coming in fit into a particular dimension. So we need to do a little bit of processing over here. And that processing that we do is very, 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 very important, because if you don't do that, we are going to be in a lot of trouble over here. So over here with this data, if I'm to check maybe the data type of this, you see that I'm getting it from the Python image library, blah, blah, blah. I can do a type conversion into, let's say, data array. Okay, it's going to be equal to np.array. And then I pass in data over here. Now, if I'm to do data underscore array this way, you see I have this, okay? So this is basically that. And like I did indicate, maybe this number, okay, based on what we know. So let's put this over here and see the color combination that we get. If I'm to put these numbers over here, let me drag this a little bit here. So, oh no. Okay, so the first color, the first number we have is 103, which is for red, 103. And then the second one is 91, and then blue is 75. So that's this color, okay, this color. And then if you are to look at this, yeah, we can actually have a intelligent guess that look, this is practically almost the same as what we see over here. So we can check these things, okay? All right. So we are rest assured that the image is exactly what we are getting in terms of its matrix representation. And then we can go on and on to do some manipulations of it. But look, like I said, when I do this and I do the shape this way, look at the shape. The shape is also once again coming from the dimension when we did the hovering around it, okay? And then we saw this one is a colored image, so we are seeing the color channels over here. Now this is for image mail 3, is that okay? Mail 2. So let me just paste this, copy this, Control C, and then put it somewhere here. So this is mail underscore 3 is this. Let's do mail 2. So for mail 2, if I run this, now this is mail two, and then I check the data dimensionality, mail underscore two is having this. So there's a lot of inconsistencies over here. And if you are to critically look at every image one after the other, we are going to find that, look, almost all of them are going to have different dimensionality. And that's not what we want, because if we leave it just like that, then once again, like I said, even when we are doing multiplication for one particular image, the multiplication must be different from the other one, and that's not going to help us. So we want a situation where there's some level of consistency. All right. So in order to do that, we are going to use this one, okay? The image data generator we have imported as IDJ. And remember, we are getting this from Keras, and is probably coming from pre-processing, is going to do some pre-processing for us. So that's basically what we are interested in. So if I'm to come in here and then do, for instance, maybe, okay, so for my trained data set, okay, for my trained data, I want to have the IDG, okay? And then what do I want to do? I want to do a rescale. So I want to do a rescale of all the dimensionality. And the rescale I'm interested in is I want to have it as 1 divided by 255 over here. So this is a rescale I want for the trained data. And then let me also do same for the test data. Sorry. So let me do test data over here. So test is also going to have a rescale over here. So I run this. And bear in mind, I'm going to use these in other things that I'm going to do. Okay. So for instance, the trained data set is going to be equal to this trained data that I've done the rescale. Look, as it stands, when I do a preview of this, we see that this is basically getting its being, okay? It's an object getting it being from pre-processing, and I want to do something with it. Okay. So what do I want to do with it? I want to use this, okay, and then do a dot, I think there is flow data frame or directory. Yes, I'm getting this from a directory. And then the directory I'm getting this from, remember the directory from which we are getting the data, okay? This directory. We are getting it from image data slash training slash mails, okay? Something like that. But if we do slash mails, then that means it's going to only target the mails, but I want the entire training set. So what we are going to do is I'm going to bring this directory over here, and then I'll leave it like this, okay? When I leave it like this, basically what I've ended up doing is I just want to have the entirety of the training bit of it, okay? And then I'll do a comma. The other parameters I can pass over here. So I want to have a target size. So the target size of everything that I want, so that one does not become, for instance, this size and then the other becomes of this size. I want to have all of them in one particular dimension. So the dimension that I want for this one is I want everything to scale down to 200 by 200, okay? So that there's some uniformity over here. And then the other parameter I want to specify is the batch size. So these are parameters you can play around, but once again, it also depends on the kind of the volumes of data you are dealing with. Okay, if you have a very large data set and your batch size is very small, that means the data is going to move in that small number of chunks. Okay, so that may result in very large computational time. And then if you want a situation where your batch size is very huge, it also will have a ripple effect on the kind of things that you are working with. Now, we also want to specify a class mode over here. And the class mode we have is binary. This one makes sense because we are dealing with males and females. Now, this is going to work out a lot of magic for us because we don't have to manually do a lot of things over here. So let me duplicate this and then let me also create one for the test. So I'll change this to test and then this one will also get this from test and then I'm going to get testing over here. So basically all I'm trying to say is, look, I want to scale things down, okay? And from that scaling, I want you to go through the directory, look for this particular directory, go into the folder, and then whatever image you have over there, I want everything resized into this target size, okay? And I'm interested in passing things in batch size of 3. And then the classes I'm working with are just 2, so I need a binary class mode. So when I do this and run this, we don't seem to have any problem. So you see that we have a preview of whatever thing that might have happened over there. And it is telling us that, look, it found 36 images belonging to 2 classes. Remember, for the training side alone, you could see that the males were 18 images and then the females were 18 images. Put them together, we have 32. Okay, sorry, 36. And then the classes were 2. Okay, so it is automatically going to do a lot of the work for us. We don't have to reinvent the wheel and do so many things over here. All right. Now we can also look at a few things over here. Okay. And hello.
Yeah. I want to find out, resizing the image, won't it affect its quality?
Okay. Thank you very much. So yes, ordinarily, okay, resizing of the image can affect quality. Okay, it can affect quality. But one of the things I also tell students is, let's look at the image. Oh, let's look at the image. So there are basically 2 things over here. There is one we would want to refer to as resizing and then reshaping. Okay. So I can have let me open. I don't want to tamper with one of these images over here, but then let me come in here into my downloads. Good. So I still have this image over here. Okay. So this is still the image. When I do a right click and maybe go to paint. Now, this is the image. We know that there's some matrices behind the scenes somehow. Okay. Now, what I'm going to do is, let's say I can do a very good a resizing over here. Now, when we look at the pixels version of it, this is where we actually get to see the things very well. So you can see that for the horizontal stretch it is 531 and then the vertical stretch is 306. Okay. Now, what I want to do is, if I come in here and do maybe 200, and let me uncheck this one so that's the ratio, because that's basically what you are trying to do. When I do 200 by 200 and click on OK, the image is definitely going to be resized, okay? So when I do OK, we have this resizing over here. Now, what this basically means is let me zoom in. For instance, if this, before it resizing is red, after resizing, it is still red, one way or the other, okay? The actual data is not lost, okay, unless we do what we call a compression of the image. When we do compression of images, yes, some significant chunk of the data is lost because of the fact that sometimes you compress images and you see that even the colors are fading now. And that's simply because the intensity of those colors are dropping. But then when we do a resizing, as we are currently doing it now, it is basically going to just change the dimensionality and then things are not going to really be affected. Now, at the end of the day, okay, assuming something is affected, Okay, assuming something is affected, what we've ended up doing is we have actually done what we call scaling. So that effect is not just going to be on one data, it's going to be across board. So for instance, if everybody is having 100 CDs and I slash each and everybody's 100 CDs by 2, yes, the money has reduced, but the effect, nobody has become richer than anybody. We are still at the same level. And that's exactly what we have over here. So yes, the data may change if you have to look at it with a microscopic lens. However, because it is across board, nobody is going to be affected. Please, are we on the same page?
Yes, I think that's fine.
All right, thank you very much. So that's what we have over here. So we have done the resizing and then we see this, okay? All right. So now we can move on to building the model and seeing how things will work out over here. So this is where we actually build the model. So let's build the model over here. So model development. So we are going to say from keras.models, I want to import. And remember, we imported this when we're dealing with a shallow neural network. So we imported a sequential model, and that's exactly what we are going to do over here. And also from keras.layers, we are going to import, and this is where we import. Back then, we used to import only the dense layer, okay? Over here, we are going to import dense, we are going to import flatten. We're also going to import this one called conv 2D, and then we are going to have max pool. So I'm going to explain each and every one of them as and when it becomes necessary. P is capital and then 2D. So these are the layers that we are going to have over here. And you could see that we need some of this, okay? Like I said, as we build this, I'm going to explain each and every one over here. So let me run this and then we have some problem over here. So I think the spelling of flatten, okay, so there's no R over here. Okay, so we are good to go. So now let's create the model. Like I said, the first thing we do is basically to get the skeleton. So the skeleton is going to be a sequential.
What do you want to eat?
So a sequential model this way. And then the next one is we start adding in the layers. All right. So I'm going to do model dot add. What do I want to add? The first layer I want to add is a conv 2D. So a conv 2D, I want to add a conv 2D layer. And then as we already know, whenever we add these layers, we need to specify, how do you call it? The kind of parameters that we want for them, okay? So over
Okay.
here,
Looks like you can't see your screen again. So
oh, sorry. Let me stop sharing and share again. Please, can you see it now? Please, can you see my screen now?
yes.
All right, thank you very much. So we have a conv 2D layer over here, and I'm going to explain what this conv 2D is doing. And then we are going to have what we call a parameter we are passing over here. So this is what we have as a filter, okay? And in this filter, we'll come back to this. Sorry, in this filter, we'll come back to what this filter is doing. And then we're also going to have the what you can also call the dimensionality of the filter, okay? And then the usual suspects are activation. Let's start with a ReLU over here. We know what this ReLU does for us. And then the input shape. Remember, we dealt with this input shape earlier on when we were dealing with the iris tools and all those things. So we also have the input shape that we need to specify over here. And in this input shape, you realize that because of uniformity over here, okay, and the fact that for our target size, we are doing a 200 by 200. And remember, these are colored images, okay? So our input shape is definitely going to take that form. So I have 200 by 200 by 3, okay? All right, so this is the first layer that we have. All right. Now, let me explain this convolutional layer and the parameters we have over here. I'm saying that we have a filter over here and what this filter is doing for us. All right. So let's assume we have established some few points over here, okay? One of the points we have established is, look, we are going to have a tensor, okay, a very large matrix. And let's assume this is the entirety of that matrix, very big, okay? Remember, we have specified a 200 by 200 over here. So let's say this is a 200 by 200. Now, we have the filter shape over here. And the filter we are seeing, we have specified 16. So that means we are going to have 16 filters that are going to filter the numbers that we have over here. So 16 of them. So let's say this is the first one coming in. And this is going to be a 3 by 3. So if this is a 200 by 200, okay, there are 200 numbers over here, okay, in terms of the rules, and then there are 200 columns over here. So this filter is going to take it section by section. So the first 3 by 3, and then it will do some computation over there, okay? And then it will move on to the next 3 by 3, it will do the computation all the way to all the 200 by 200 for the entire thing, okay? So it's almost like spreading, for those of you who grew up in the village, maybe you understand what I'm saying. You see, when our grandfathers used to dry their cocoa, okay, they'll spread the cocoa on the mat, okay? And when they do the spreading, they now focus on session by session to now filter out what maybe some debris or maybe some impurities that may not be needed. So we spread things out. That's what we have over here. And then we put in a filter. So we go through it session by session. Now, what this filter is basically doing is, look, we may have, let's say, a particular section where the numbers showing up over there. And I'm going to use small numbers so that we don't get confused. So let's say the number showing up over there is 2, 1. For simplicity's sake, let me just use 1, 2, 3 and stuff like that. So let's say I have 1, 2, 3, 4, 5, 6, 7, 8, and then 9. So this is data from the original entire 200 by 200 shape tensor that we have over here, okay? And then the filter, which is going to be some randomly generated matrix of a 3 by 3 shape, is going to have some random numbers, okay, in that 3 by 3 shape. So let's say we have 1, 2, and then maybe 0, and then maybe 0, negative 1, 5, okay, maybe 1, 1, 1, random numbers. So this is going to go through all this 3 by 3 nature, 3 by 3 nature, and then be working out some magic. So what is going to happen is each element over here is going to multiply its corresponding entry over here, okay? So this will multiply this, so you are going to get a 1, and then this will multiply this, you are going to get a 4, and there's going to be a summation at the end of the day. So it's going to be 1 plus 4 plus, and this will multiply this, we are getting a 0, okay? That's for the first row. Now this will also multiply this, we are getting a 0. Now this will multiply negative 1, so we are getting a negative 5 over here. And then this will multiply this, we are getting plus 30 over here.
Now this will multiply this. We are getting a 7. Now this will multiply this. We are getting an 8. And then the final one, we are ending up with a 9. Now at the end of the day, everything will be added. So over here, we get a 5 over here. Then 5 plus this one will cancel out. So we end up with 30. And then 30 plus this, we are getting a 37 plus a 17. Okay. So we are getting this plus this is going to be 4. And then we are getting a 54 over here. So at the end of the day, when the filtering is done, we are going to get some number as a 54. And that 54 is going to be projected. Basically, when you filter something, okay, you get some kind of a new refined product, okay? So this is more or less like the new refined product. So this is going to be from the first 3x3. The second 3x3 is also going to produce a number, and all of them are going to produce some numbers, and then we are going to have a new kind of, how do you call it? A new kind of matrix, okay? Now, why is this filtering important? This filtering is very important because, look, let's assume we are trying to classify and distinguish between maybe human beings, okay? But then every person you have in your data size or data sample is a twin. So they are going to be very identical. You want to learn inherent patterns. Look, the least change you want to identify. And this is what is going to help you identify the least change, because remember, this is original data, okay? And that original data, look, in terms of color intensity, the color intensity may be from 100 and 101 may not be quite conspicuous in terms of it being very glaring, okay? It is going to be very, very difficult for you to come out to say that, look, this color is red more than this, if you are to look at it from 100 and then 101. However, when we sum everything up based on whatever thing we have over here, the final number we have, when we get 54 over here and the other one we get maybe 50, then we can say that, look, this 50 is different from the other first one we did the computation where we got the 54. Once again, back to the same point I made earlier on. At the end of the day, it is the same values of the filter that's going to run through this and the other images, okay? So at the end of the day, it is a scaling process and not necessarily one is going to be multiplied by this number and then the other is going to be multiplied by the other number. So this Com2D works out this magic. And over here, you can see that you have specified 16 of these filters. So these 16 of these filters can come in very handy, because what it basically does is it is going to help identify edges. Because for edges, like we saw earlier on, okay, this particular image, we saw that before we did the resizing, okay, it was very difficult when we look at the edges or the edge points over here, okay? So it was very difficult knowing whether it is green or blue. But when there's a Conv2D layer, which is filtering this, multiplying by some number, so that at least we get one particular number, we can now make the proper assumption that this is different from the other. All right. So now let's go back to the development of our model. So let me get rid of everything up over here. So this is our first layer, and then let's move on to the next layer. For the next layer, we are going to use model.add. Now the max pool, okay, this max pool 2D that we are going to bring in is not necessarily a neural network layer, okay? This is basically shrinking things. And I think there's an image over here that we can always look at. I don't know if it is here.
So all these resources are made available very good. So that's basically what we have over here. So for instance, we pick up the first input, this particular image, we are looking at it from, let's say, a 28 by 28 by 1. So you see that these are basically black and white images. So there are no color channels that we want to show up over here. So we are saying that for the kernel, we have a 5 by 5 kernel, okay? So this 5 by 5 will pick up, okay, and that number will be multiplied, and then we are creating a new 24 by 24 by n number of channels, okay? So it's basically going to break it down, kind of going to break the image down into smaller chunks. And then the max pooling, this is a 2 by 2 max pooling happening over here from here to here. So this is basically going to shrink the numbers down. So you could see that from 24 by 24 by the number of channels, we are getting a 12 by 12 by the number of channels. And then we go, so the max pooling basically shrink things down, okay? It's basically compresses things down. And what that actually also means is there's some kind of, they call it, there's a technical word for it, but it's almost like voting, okay? It's almost like voting. So the matrices, the numbers in there will kind of vote for the maximum value, okay? And that's where we get the name max pooling, okay? So it's like the maximum value is pulled out, okay? Now, what that basically means is, look, we are dealing with images, okay? So if we have numbers, and these numbers are not just random numbers, but then some number representation of some colors, okay? Like I said, if the RGB color combination, let's say for red, the maximum or is 255, okay? So if we have 255 and we have maybe 200, okay, all competing for space, and we want to have a number that will represent that particular region, we'll definitely go with the maximum, because the maximum is a proper representation of that particular color. That's I mean, one of the ways I use to explain and also understand that particular concept. So the max pooling is going to help us pull those numbers. So for max pooling, we bring max pooling over here, and then we specify a shape over here. So we'll do a 2 by 2 here. And then the next one, we are going to go back to the conv2d to also do some filtering for us. So let's bring this one down. And then this time around, let's say I want to have 32 filters, 3 by 3, and then let me leave this as relu over here. And at this point, I don't need an input shape because the input shape is already sorted, okay? All right, so I have this, and then let me also bring in a max pooled layer over here. So over here too, I bring this one over here, and then it goes on and on and on and on, okay? So the number of layers you put up over here also depends on the kind of network you are building, okay? So once again, convolutional. Remember the earlier definition of the word convolutional that we spoke about was the fact that at the end of the day, we are interested in multiplying things, okay? Putting things on top of each other and stuff like that. So that's where we get that inspiration from. All right. So let me quickly run through this so that we can at least build our model and see how this one works. So let me also bring a max pooled layer over here. And then the next one is, now let's flatten things up. Okay, so I'm going to do model dot, and this time around, I want to add a flatten layer. So model dot flatten this way. So why do we need this flatten layer? Now look at this. This flatten layer basically will shrink everything back down into now we are trying to move from the matrix, okay, to like a vector, okay? So let's stretch things up, okay? And in stretching things up, back with the example that I use, look, when we do a resizing or when we do a stretching, we have not taken away any color, basically. So things are still going to be represented in terms of the numeric values as we have them over there. So we have the flatten layer, and then let's now bring a dense layer. So let me do model.add. And with our dense layer, we are quite familiar. So let's say we bring in these number of neurons over here, and then let's bring activation. Sorry, activation as ReLU over here. And then finally, we bring in a model.add. And over here, we bring in another dense layer. And in here, we pass in one output, okay? We want to do binary classification, just male or a female. So activation is also something that we are going to change over here. So over here, we are going to use sigmoid because we are dealing with binary classification. So we just want either this or this. Remember the sigmoid activation function, the output is either going to be some kind of a 1 or a 0. So I run this and then we don't seem to have any problem.
Can I come in, please?
Oh, yeah, sure.
Okay, all right. So if you go back a little for me on the diagram.
Okay. Is it this one?
Yeah, right. Okay. So the summary of the whole thing is that we can use shallow neural network or deep network neural network to do what it's trying to do now. We can do that. But the image that we have seen now, you see that the image sizes, some of them are uh, uh, 700 and something by 1100 and something. Now, so what it means is that in the model deep network or shallow network computation, we have inputs that we apply to the network. Now, so if we want to apply, we cannot apply directly the two-dimensional or three-dimensional image to that network. So what you have to do is you have to convert it or move it, change the shape of that data from two-dimensional to a one-dimensional data. So what it means is we're going to have, if it is image size is 600 by 1100, then we are going to have 1 by 600 times 1500. So that number means that each of these elements are going to be input features that you are going to use for your development. Now, so this type of dimension is so huge. It will require a lot of computation. So what we try to do is, this is where before convolutional neural network came, that was what we were doing. So now with the availability of convolutional neural network, it helps you to shrink, or we call it the compression, to reduce your data size from, instead of 1 by 600 times 1100, we are now going to see if we can reduce that data to something like 1 by 400. So that at least the input you are going to have is going to be 1 by input of number 1 up to number 400, rather than having number 1, number 2, number 3 up to 600 by times 1000 elements that are going to the network. So this is what the convolutional network tries to achieve. So when we take the input and we multiply by the kernel, of course, because of the different shapes and then the edges, shapes and edges, we need to have, you see that the second element here, we have a number of layers in there. From the letter 2, we have a kind of volume in here. And also this volume, the various types of kernel, the kernel we have there, they are random entries. So we're going to have different random entries of 5 by 5. And as they multiply the image, we are going to have different effects. So those cumulative effects, that gives us a volume we put together. Now the next one is the polling. So if you see the 2 by 2, if you see the image, the letter 2 here, that is 28 by 28. Now, the 2 by 2 here means that we are going to find 2 rows, 2 columns. And those 2 rows, 2 columns, we'll look at what is their maximum value. And that maximum value here will represent that 2 by. So instead of having 2 by 2, we are going to just have 1 point only, representing the whole 2 by 2 element there. So we scan it across the image, horizontal and vertical. So this 28 by 28 eventually may be reduced to something of the order of, let's say, 12 by 12 or 10 by 11 by 11, sort of. So we have reduced that size of the image. So depending on what type of architecture you want, you can, if you think that, see that he did the kernel, then that has a dense, then he did the pooling, dense, pooling, pooling. So it means that you are trying to scale down as you go along to your image to a certain reasonable size that you have, that you think is okay. Once you think is okay, then you can do the flattening. So what the flattening does is it now resolves, it will still, at this point, will still be 2 by 2. It will still be a n by n two-dimensional array, but it will be a reduced size. So what the flattening is going to do is to move it from that n by n into 1 by n squared after we have done further reduction. And that is what it was trying to do over here. So that is how the convolutional neural network works. So if you think, if you see, for example, things like the YOLO that we use for image computation and various things, they have related architectures of CNN that they are using. So some have about 4 or 5 layers of what we are doing here. Maybe convolution layer, pooling layer, convolution layer, pooling layer, in that order. And the final point is, it is not only the max pooling that we use. There are 2 types of pooling that we use to help us reduce the data, called data reduction. One of them is the max pooling. So if you take 2 by 2 matrix, we'll look at what is the maximum value. And that maximum value, just one element only, will be used to represent that 2 by 2. Another option that we have is to call mean pooling. So these are the 2 that are used, max pooling and mean pooling. The mean pooling here means that we'll find the mean of the 2 by 2. So all their elements, we add all them all together and it will divide by the number of elements. And that will give us the max pooling, which will represent that data that we have. So that is how the operation works. Now, because the kernel that we are using is a random entry data, we may have both negative and positive. But when you have an image, we don't have a negative image value. So this is where we use the ReLU. So that the ReLU function, from the beginning, we talked about those functions. So the ReLU function would make all negative values 0. The ReLU function behaves like a linear, but without the negative element. Just like we have in your basic electronics for rectifier. So that is what it does. So only the positive ones are taken as a linear function. Very good. So f of s is x. So if s is 30, f of s will be 30. If s is 100, as long as s is greater than 0, any of value of s less than 0, it forces f of s becomes 0. So all negative values are zeroed and only positive values are kept. Now, so the final one, the dense that he was talking about, you see that, Ken, can you type for me the sigmoid? Sigmoid gives us a value that is between 0 and 1, but includes points. So you can have 0 0.1, 0 0.2, all the way up to 1. So if we are looking for functions that will give us only 1 and 0, then one option we have is to use what we call a signum. Signum will give us 1 or -1, or a unit threshold. Unit threshold will give us signum, signum. No, right, okay. So signum will give us this 1 or 1 or -1 or 0. So if you look at the curve, you are going to have minus and then positive. So it is either 1 or -1. But if we want 1 or 0, then we use the unit threshold or hard limit. That unit threshold or hard limit will make it either 1 or 0 for us. But if we use sigmoid, then sigmoid will, just like the 1 over 1 plus e raised to the power minus x, we can have values that range from 0, 0.1, 0.2, 0, all the way up to 1. But we don't want to see 0 point something. So we then resort to either a signum or a unit threshold or unit function. And that unit function will force it to either 1 or 0. So can you please type hard limit? Hard limit function. Okay. So hard limit function will give us this. +1, that's 1 or 0. That's how we get it. Hard limit function will give us 1 or 0. Or some also call it unit step, something like the unit step function. So that is what it is. We can get 0 or 1. So if we want something like this, then we can check with the, as MATLAB has those functions. So we can check from Python and see whether it has a definition for hard limit. Otherwise, if we use a sigmoid, then we are going to get 0.1, 0.2 in that order, up to 1. So that's the contribution I wanted to add to it. Thank you.
Okay. Thank you very much, sir. All right, so let me quickly wrap this up because our time is up actually. So let me just run through this and then compile the model and then we'll see how this one works. So if I'm to do model dots, and this is something we've done before. So model dot compile. And then we pass in the parameters that we know. So optimizer. And this time around, we are going to use an optimizer called the roots mean squared prop or propagation. Okay, so let me just do a Google search on this so that we have an idea of why we need this. Now, we need this because this optimizer works very well with the convolutional neural network architecture itself, okay? So this is an adaptive learning optimization algorithm for neural networks. And if we are to go deep into its popular usage and stuff like that, you are going to see that, let me just do use cases. So we are going to learn that, very good. So the primary user in recurrent neural network, okay, and then convolutional should be somewhere here, somewhere. All right. So that's the optimizer I want to use for this one. And we need these optimizers because without them, our model is probably not going to converge, okay? We need some point of convergence one way or the other. And then let's specify a loss function over here. So the loss function that we are going to use is, we are going to use binary cross entropy. So binary cross entropy, and over here, because we are doing binary classification, we need this. And then the metrics that we are going to monitor is going to be accuracy. So these are things we saw with the other ones, okay? The other ones, I think the loss function we used was sparse categorical cross entropy for the Aries flower classification. And then the optimizer we used then was the Adam optimizer, okay? And then we still checked out on the accuracy. So now when I do model.fit, this is where I now bring in my training data. And my training data is what I have over here, okay? This training data set. So I'll bring this training data set in here. And then I'll specify the number of epochs. So the number of epochs, the number of iterations, basically, let me put 10 over here, and then let's run this and see. All right. So it is running, and looking at how fast it's running, maybe in the next 2 minutes, we should be done. So we keep monitoring what we have over here for the accuracy, and then there seems to be some marginal improvement in terms of how well our model is learning, and then we are getting about 94% over here. This is 91, so it is doing quite okay. So we finally end up with 100%, okay? Well, the data set is very small, just about 36 samples for our training and our testing. So there isn't so much learning to be done. But in the real world, when we are working with maybe data set for your projects and stuff like that, you are definitely going to have a lot of things happening in terms of the numbers. Now, what I'm going to do is I'm going to put myself to the test. So I have some personal images over here. You can also try with your own personal image, okay? So that we actually check. Let me look for the images and then I'll continue with the screen sharing. So I have some images over here. I have a passport size image. Maybe we can use this one. So I'll copy this and then bring this somewhere here. Where is this? Okay. All right. So let me share back my screen. Okay, so I have this image, which is my own image, okay? This is a passport size image of myself. And I've done some training. The model is telling me that, look, I can give you some 100% accuracy in terms of binary classification, whether somebody is a male or a female, okay? And I want to figure things out. Now, the model has been built, everything is looking good. Now, let me try and bring this image over here and then pass it into the model to do a prediction for me to see, okay? So let me have this as test data. So the test data, we can do a number of things over here. So remember, in order to bring this, okay, we did image.load. So I can bring image.load over here. And then the image I'm looking for is test underscore data. Let me look for the file extension. Let me see. So the file extension is JPG, okay. .jpg. So I have a problem over here. Oh no. The name of the file is, I think, rather Ken Bruni. Yeah, Ken Bruni. So let me change the name over here to Ken Bruni. So Ken Bruni this way. Okay. So if I'm to do Control C, Control V over here, this is the image I want to test. Remember, this image is not part of the images I use for the training. So I want to actually check if indeed this is going to work. And in order to also get the metrics version of this image, once again, I can do, let's say the test data is going to be equal to np.array, and then I pass in test data. So I've converted this into the metrics version, and then I get this, okay? I don't need to worry about this number. But then the interesting thing is, with this test data, when I do a .shape, this is where it gets interesting. The shape I'm having over here, probably none of the images I used, the original version as they were, okay? None of the dimensions were of this nature. However, because I did a resizing,
and I made some uniform resizing. And in fact, when I was building my model, I also made sure that, look, every data that comes in fits into that dimensionality. I also need to kind of change things up over here so that there is some conformity so that I can use that in testing my model. So the way I have to do this is very simple. All that I need to do is to now change the dimensionality over here. So over here, there are a few things we can do. Look, if I'm to do test underscore data dots, let me check the type of data I have here first. This is a NumPy, so test data dot, let me say resize. Let me do 200 by 200 by 3. If this is going to work, we don't have a resize function. Okay, let me do this. There's supposed to be a way I need to do. Let me see the size. Let me see this. Okay, so there's a way we go about this, and let me try and see if I can figure that one out. Let me just do a Google search of this so that we can quickly, so resize NumPy array. Okay. So I was doing a resize to modify and then create a new. That wasn't working. So okay, so aid or resize and then the new shape or reshape of, okay, np dot resize and then this. Okay, so let me try that one and see. So np dot resize and then I pass in the test data, and then the shape that I want is 200 by 200 by 3. Let me do this. Okay, so this one is looking good. And then let me save this back in test underscore data. So now when I do a preview of the test data, I have this. And the most interesting part for me is when I do a dot shape now to check the shape. And now this by this by this by 2. Oh, so I wanted by 3. Sorry. So let me run this from the top to get everything working properly. So let me run this. All right, so now I have my test data as the 200 by 200 by 3. Okay, so I think this one should work. All right, but there is a problem over here. Okay, and let me just run this through. The problem will come and then we'll fix it, and I'll tell you why that is happening. So if I'm to do model.predict and I pass in the test data, which has now been shipped in its proper format, okay, for things to work, we get a problem over here. And when we scroll down, you see that, look, the input 0 layer, okay, which was from the sequential, is incompatible with the layer that we are working with. Now, the expected shape is a none by 200 by 200 by 3, but it got a none by 200 by 3. Okay, when we check the shape, we are not seeing a none over here. So there is a problem. And I think every year when we do this, I try and explain this to students. So over here, we need to do what we call an expansion. Okay, so let's say the test data once again, and then we are going to do np dot
we are going to expand the dimension. So expand underscore the dimension this way. Okay, so what do you want to expand? We want to expand the test data, the data itself, and then we specify the axis as 0. So basically, anytime we have an axis as 0, that means we are dealing with the row, and then an axis as 1, we are dealing with the column. So when I run this, now this one is looking good. Now, it is still going to be the same number, okay? It is still, going to be the same matrix one way or the other. But now, if I'm to check dots, shift this way, now we see that we have 1 by 200 by 200 by 3. Now, this 1, in terms of the expansion of the dimensionality, this one is very important. It's basically telling the system that, look, we are just passing one stream of data, because if previously we were just passing 200 by 200 by 3, so the system was a little bit confused trying to figure out this 200 that is coming in, is it representing one image, or maybe it is representing 200 different images, okay? Because just a dot can be a color combination, that can be an image I want to represent. So when you have this way, it basically tells the system that this whole thing, consider it as one image and then pass it through the system for us. So now if I'm to do model dot predict, and I'll pass in the test data, when I run this, we get a value of 1 over here, okay? 1 basically tells us that, because look, we use, how do you call it? The sigmoid, and we use just 1 neuron for the output. So it is basically going to give us just 1 output, okay? And 1 figure, and we are using sigmoid, so either 0 or 1 or some value of that sort. And we are seeing 1 over here. Now, how do I know that 1 is for male and then 0 is for female? We get 1 for male and 0 for female from, sorry, I didn't show you that. But then when we did the processing of this, as we have over here, okay, there was something I think I should have touched on. I probably skipped. Let me try and see if I can bring it back. Now, whatever data we had over here, which is, for instance, maybe this one, the trained data set, okay? When I do this and I do dots indices, let me see, dots indices. I don't know if this one is going to work. No, not dots, just one. Is it index? Let me see. So data sets dots. Very good. So okay, it's class indices. Okay, when I do class indices, we see that the 0 was giving a class index of female, and then the 1. So anytime we do a prediction and then we get a 1, we should know that this is a male. If we get a 0, this is a female. That's basically what we are getting over here. Now, how is the system able to know that, look, the image I presented in terms of my very image over here is a male and not a female? And like we are trying to explain, the whole point of trying to use convolutional neural network is to find some inherent patterns. So maybe the kind of features it was able to discover, looking at the max pooling and all those things that we spoke about, okay, it realized that, look, for most of the males I analyzed, the inherent pattern I saw is the fact that they don't have long hairs, because I don't see long hair over here. So that's one of the descriptive features it can. We are just saying may, because it has a lot of things it will look at, okay? Maybe for a lot of the other females, there were not, a lot of facial hair, for instance, have beard. None of the females had beard. So upon doing the analysis, realize that, look, in terms of this area of an image, there is no beard or there's no lot of hair for the females, okay? Even though there are exceptional cases, but at least for the data I presented, there are no instances of that sort. And it moves on and
Hello,
on.
Ken. Can I interrupt, please?
Oh, no problem, sir. You may.
Please, I think the time is far. We almost get 30
Yeah,
minutes.
sure.
Some of them are preparing to write tests. So
Okay.
if we can. so that Friday we can continue and wrap that one up.
All right, okay. Then I'll leave it here because there are a few things I also want to bring on more. So definitely Friday we'll wrap everything.
Friday we can conclude on that, and then
Yes.
we give some trial work for them to look at.
Exactly.
Thank you.
Thank you very much. All right. So please, if you have any questions, just put it down. Friday when we come, we will discuss these things. And let me also point out that I think the source code for everything I've done over here is something we did the previous years. So I'll share the source code with you, okay, so that you can also practice along. So that Friday when we meet, if there are any questions, we'll discuss them and then we'll move on to the next one. Okay. So thank you very much for your time, and then we'll meet, God willing, next week.
Thank you, and good night to everyone.
Okay.